Okay, this is the building. This is our building, and this is the PV array that we have here. And as you know, well, we can have like a PV array 3 times as big as this one. Okay, so why did they decide just this PV array? Well, because it was expensive back. Now probably it would be, no, but it's even expensive because you have to create the structure and then you have to cover that structure with the PV panels. It's an open rack, so it's not a roof mounted array. A roof mounted means that you are in contact with the roof, so you have a slope, you have a roof with a slope, and then you place the panel just on the roof. But with this open rack, you have a flat roof, and then you have another structure, and so this is what means an open rack PV array. Yeah, Evan, don't worry, because I will open let me know when you're available, and I will open the quiz for you. So this is the first thing. The PV production will increase with this solution, but it will be more expensive than having a tilted roof and then placing the PV panels on it. Anyway, let's analyze this. As you see, it starts here and it ends there. So if we look at the grid lines, I think this is the starting point, and this is the, which one, this or that? Yeah, I think it starts here on this grid and it ends there on that grid. This volume, it's out of the, yeah, it's out of the PV array. Kind of. I don't want to be extremely accurate, but yeah, I think this is the grid, the first one. We don't need this 22, and that will be the first. If we open level 5 or level 4, let me see the levels. Okay, so on level 4, we have the roof. This is a flat roof, and then the structure has to start there. What is the slope? I think the slope is around 25 or 30 degrees. I'm not sure. Anyway, if we create the 3D view, this is north-south oriented. So this is the south, and the slope for sure is south oriented. I'm going to hide the sun path. Okay, so we have to create like a plane here. How can we do that? Well, we can go to the east elevation, and the easiest way just to start trying something is to create like an architecture roof by extrusion. We have to select one of the grids. Let's say grid, I think we started in grid 2. Okay. Level. Yeah, I would say level 5. And now we just can do this. And the angle, I told you 30. No, 30 is too much. I think it was 20. I have to find out this angle. I'm not sure yet. And then we have to select the roof. Something very thin. Okay, I'm going to select this one, but I'm going to edit type, and I'm going to duplicate, and I'm going to create a roof just a 2-inch roof, and the structure will be 2 inches. And now I click finish, and I have a thin roof. I want this roof just to fit the PV panels, or just to perform this PV array. Well, that's the, when we talk about the PV potential, I mean, if we had this PV array, we could create, or we could, yeah, so this is the PV potential. This is the footprint of the building, and this is the maximum area that we can have. But in this case, we don't have all this roof, and I think we should start here. Yeah. Something like that. We don't have the structure yet. We are not going to do it today. I just want to analyze the potential of this building. Let's go to the east elevation. And if we go to annotate, and if we go to the angular, we can select this point and that point, and here we have the angle. The angle is 20. We can change it if we want. This to be 15. So we can change the angle. And I have to find out the real angle, because I think it's between, I told you it was between 25 and 30. No, it's between 15 and 20. And one of the things that we are going to study now is the PV potential. If this is the best PV potential that we can have. Okay, so I don't know, it's 15 or 18 or 20, something like that. And how can we do this? Well, now I'm going to do this with the PV watts. Okay, so I'm going to analyze the PV potential. And we can do this with Revit. We know how to do it. Now we have to go to analyze solar. We can select solar energy annual PV, cast user selection. So I want to select this. Yep. And then here, finish. Cumulative insulation. I want PV energy. I want kilowatt hours, because the PV, we have to compare, and the PV outcome, it's always in kilowatt hours. Solar analysis annual. Okay, so we can update. Okay. So this is the total. We have 821 square meters, because we are working in international units. And this is the kilowatt hour per year. This is the PV energy production. So as always, I'm going to take a screenshot of this, because now we have to compare this to our PV watts study. Okay, so this is all the information we need. We have 821 square meters, and this is the total PV production per year, 180,000 kilowatt hours per year. Then we have to compare this production to the energy demand, and then we will see if this is around, it has to be around 30% of the total energy demand of the building. Okay. But that's it. Is it the best angle? I think we agreed that if we work with an angle close to 40, I think the yield will be better. Can we do this? Well, in theory we can, but is it feasible having this with this angle? Let's do it again. Let's work with the user selection. We are selecting this. We have the same area, so we have created that roof, and we have changed the slope, but we have the same area. So this is what I want to compare now. I finish, and I update. And this is more, it's 195. So would you do this? I don't think the municipality allows us to do this, and it will be extremely expensive because we need another structure, and now this structure is going to be much higher than the other one. So sometimes this is the best option in terms of PV production, but it's not the best option in terms of architecture design. So that's why we need to balance both things, the PV production and the architectural design. So not always the best PV production is the best decision in terms of architecture. But anyway, we can take another screenshot here. And we can place it here. And now the difference between this option and that option is the angle. So I'm going to insert text. This is the angle. It's 15. And here the angle is 40. Okay. We can try 20, 25. So first we need to we need to take into account what we want or what we are allowed to, because sometimes the municipality doesn't allow you to go that high. So you say, no, the maximum height of the building should be this. So you have to abide by this rule, by this municipality regulation. And then you can decide the angle. Maybe 18 would be better, because we know that from 15 to 40, 40 or 45 would be probably the optimum. So 18 would be better than 15, 20 would be better than 18. But what is the total, the maximum height that we can have here? I'll find out. This is just an exercise. And now we have to we have to compare this to the PV watts analysis. I told you that we rely on this Revit analysis. If this is, I can rely on this. Okay, if I compare this angle and this angle with the same tool, I can reach the conclusion that this angle is better. Okay, because we are using the same tool. But is this the accurate number? Is this 195,717? Is this exactly the energy that we will be getting? We don't know. Anyway, if we want to compare the PV watts, I can open a PV watts calculator. Well, the first location matters here, because this is okay. Good question. Where am I working in? Manage location. This is in Boston, Massachusetts. Okay, so we have to change this to Keene, New Hampshire. And yep, this is Keene, and it's pretty much where the building is. So we click OK, and I'm going to run this analysis again. I don't think it will be very different. Okay, this is 196, and this one was 195. Yeah, it depends on the location, it depends on the latitude. So let's use Keene instead of Boston. This one, I'm using that one. And for this one, we're going to use Keene as well. So go to the east elevation. I select this. I type 15. Finish. Okay, 179. And it was 180. Okay, so here we can type location, Keene, New Hampshire, angle 15. And here we can type location, Keene, New Hampshire, angle 40. So now we have to compare this to the values that we have in PV watts. First, we need to make sure that we have the same location in New Hampshire. So it's in Keene. And okay, now we have to include the system, DC system size. What is this in kilowatts? That's why we even this PV watts calculator comes from the Department of Energy of the United States, and they are using international units. So that's why for this analysis, we have to use international units, kilowatt hours, and then the results will be kilowatt hours per square meter. So it's better if we use square meters to compare the Revit analysis to the PV watts. Okay, so here we have the module type. So for the module type, we have the standard, the premium, or the thin film. Well, I don't want to go over this today. We're going to use standard. Standard, it's a crystalline. You know that there's a crystalline and there's a thin film, or the amorphous. The crystalline, it has a better performance, but the thin film, it's, well, we don't have cells, so it can be transparent. We will explain this later. Then the array type, we have a fixed open rack. This is what we have. We have a fixed roof mount, or we have a tracking system. We don't have a tracking system. A tracking system means that the panel is moving according to the sun. We have a fixed, and it's open rack. It's not roof mount. Okay, so it's open rack. The system losses, well, we have losses because we are generating DC, direct current, and then we are transforming this into alternate current. We have losses. We have losses in the transportation through the cables. So they evaluate this as 14%. Okay, that's fine. That's fine. It's something we cannot have 100% of production of the energy that we transform in electricity. We cannot use 100%. We always use part of this. 14% is something acceptable. The tilt, well, we have to use 15 because this is the actual tilt that we have here in this first. And then the azimuth is 180. Here, 180 is south. Okay. So this is the azimuth, is the angle, and it takes into account the orientation. If we have south, it has to be 180. And now how can we calculate the system size? Okay, because here we are not talking about the area. We are talking about the system size. And this is something that I don't know what Revit does. Well, probably Revit, there will be an explanation, and they will take into account the watts per square meter that this PV panel or this PV array is producing. That depends on the quality of the PV panel. So we can have a standard, we can have a premium, will be better, or a thin film that will be worse. Okay, so the standard is something like standard, and then we can Google the standard PV production of PV of PV panel per square meter. How much energy? Right, let's see. Multiple panel, yeah. So most panels are either made of polycrystalline or monocrystalline. We don't have the thin film. Mono and polycrystalline, it's the same. So there's a difference, but it's for us, it can be the same technology. And I want to find, okay, it will likely only produce around 150 to 200 watts in good sunlight. Okay, but yeah. So this is the average. Yeah, this is the efficiency of the PV panels. It's only 15 to 20%. That means that out of all the solar radiation that hits the panel, only 15 or 20% can be transformed into electricity. This is a very low efficiency. Efficiency is it's a ratio that measures, okay, if we want to convert something into something, what are the losses? Now we have like 80 to 85% of losses. This is not the same as this. You say, okay, but the system losses is the 14%. Now, once we have turned sun into electricity, then to transport this electricity that we generate in the PV panel to our computer, because it runs on electricity, we lose 14% of this. But out of the sun that hits the panel, only 15% of this total energy can be turned into electricity. Okay, and then we lose 14% of this electricity that we have generated. So this is not a very efficient system, and usually engineers don't like inefficient systems. They like efficient systems. Okay, if the efficiency of something is above 80%, okay, that's a good system. 15%, it's something very bad. That's why back in the early 21st century, engineers claimed that PV panels were not a reliable source because the efficiency was very bad. And if the price is very high, the efficiency is very bad or very low, then it doesn't make any sense using this technology. Now the price is going down and the efficiency is not going up. But if the price goes down, then the average performance of the technology is better. Okay? But I'm not happy with this explanation, and I want to go to Alibaba. Okay, I want to see. Last time we were looking at the price, but now I want to look at the production. Okay, so the nominal output power is 190 watts. That's yeah, this is what I'm looking for, but I want to see the size of this panel. The module efficiency, it's 18. Yes, as I told you, it's always between 15 and 20. So this is 18. So it's quite good. 20 would be better, but 15 is worse. And okay, here we have the. Usually, this is always in metric units, and this it's in imperial units. Okay, let me see if we have another one in metric units. this is metric units. And what is the, okay. So this is 375 watts. So when we're deciding the panel, we have to look at these specifications. This efficiency is 19.1, better than the other one. Okay, so we're going to use this one. 20 is maximum, but the closer we're to 20, the better. So we are using a 375 watt panel, but now we need to know the watt per square meter. So we need some math. So we have the power is 375 watts. Now the area here we have the dimensions. It's this is millimeters, so we have to divide by 1,000, and then we have meters. And this is point. This, and we have meter. This is around 2 meters by 1 meter. It's around 6 by 3 feet. Okay, so it might be different, but usually all these panels are 3 by 6 feet or 2 by 1 meter. Okay, so we need to calculate the area now. So I'm going to use the calculator. The area is 1. Oh, this is not 1,000. Sorry, this is point. So it's 1.9 times 0.9. Okay, this is 1.984 times 0.992. And this is 1.96 square meters. So now we have to divide power divided by area. And this is 375 watts divided by 1.96 square meters. And this is
191.33.
Let me do it. It's not that I don't trust you. So is this your final result?
Yes.
191.33 watts per square meter. Okay, so this is the value that we need. You won't find this value here. You can find some references here on this text. We were in this, how much solar energy we generate. It was like we have this, but looking at the panel itself and looking at the specifications of the panel, we can calculate it more accurately. Okay, so this is the panel specification. This is tested, so we have to rely on this catalog. This is the area of the panel, and then we divide the total production divided by the total area, and then we have the watts per square meter, the power per area. Why are we doing this? Because in PV watts, we have to calculate the DC size of the PV array. As you can see here in PV watts, we have the DC system size in kilowatts. Okay, so what does it mean? So we have to insert here kilowatts. And here we have watts per square meter. So we have to multiply 191.33 watts per square meter times the area of our PV array, and the area is 821 square meters. 800 square meters? Yeah, might be. Okay, so that will be 821 square meters. So that would be
157,081.93.
157,
Yes.
57,000,
Yes. 81.93.
81. This is watts, and then we have to turn this into kilowatts. We divide it by 1,000, so it's around 157 kilowatts. And this is the DC size of my PV array, 157. And this is the value that I have to insert here, 157. So this is the DC system. This is system size, 157 kilowatts, standard, open rack, 15 degrees, 180. We click results. And what is the total AC energy? AC, it's we take into account the losses, it's 191. What was the yield of this according to, okay, so according to PV watts, is 191. Well, it's not bad. This is 179, this is 191. And now we are going to do the same with a different, now with 40. Okay, we have the same size, the same DC system size. It's an open rack, it's south. And let's do this. And now the total is 205. Okay, in PV watts, is 205, and here we have 196. Well, it makes sense. This is higher, this number is higher than this one, which makes sense. And yeah, with PV watts, we have been optimistic. So I would select the lowest value to be on the safe side. Okay, so I have to keep in mind, okay, maybe, yeah, between 179 and 191. But I will use this for my calculations because, yeah, because I want to be on the safe side. If I tell my client that they can produce this and they end up producing this, they will be disappointed. But if I tell them that they will produce this and they end up producing more, they will be happy. That's a question of, this is psychology, this is not architecture. Okay, what can be the reason? Well, I know the reason because if you look at the Google Maps, this is not south, you see? It's not perfectly south, so the angle won't be 180. Probably if we change the angle, I don't know this angle exactly, but if I change the angle here, let me see, south is 180, southeast, southwest. Okay, so let's say that this is 180, let's say that is 190, 190. Probably now it will be closer to what we get in Revit. It's 203, and in Revit we have 196. Yeah, probably it's not that angle, so let's make it 200. Yeah, now it's 2001. Yep. So probably it depends on the angle, because this is not exactly 180. 180 would be the best. Okay, so we have this angle, it's not perfectly horizontal. And well, and anyway, I will take the lowest value. So if the lowest value is 196, okay, between 196 and 2000, kind of. But we cannot rely on this number because we are using different tools and we have different values. They are not that different. Okay, so this is a difference of 10%. Okay, if I want to be on the safe side, you'd better use the lowest value so that your client, if they end up producing more, they will be happier than the other way around. Okay, but this is how we are working here. First, we need to analyze what angle is the best. This is the best angle, but probably it's not feasible because from the architectural point of view, we cannot do an array like this. So we stick to this angle, and then we use different tools. And by using different tools, okay, so it has to be between this and that. If I used a third tool, and you know that we have a third tool, the PV chart, we're not using it today, but we can, okay, is it closer to this or is it closer to that value? Or is it just in the middle? So by using different tools, we can rely on the number, the figure that we have here. Again, if you have been doing this for 20 years, you don't have to think about it. You don't have to calculate anything. It is the first or the second time that you're doing this. You have to try different softwares so that you can gain confidence on your own calculations. And this is what we are doing here. Okay, so this is how you can compare Revit and PV walls. Okay, so first you have to make sure that the location is the same. Then you have to make sure that the angle is the same. Okay, first location, then the tilt or the angle, then the azimuth. Yeah, it matters. So make sure that the azimuth is the same, and then the DC system size. And before doing this, we need to find the catalog with the specifications, and we need these two numbers. We need the total production, and we need the dimensions. Okay. Here you can see that here we have different module efficiencies. So there are different names or different brands. So this can produce 365, this can produce 385, because the efficiency here is higher than that one. So I assume that the size is the same of all these elements, but this is more efficient. So go for this one if you have to decide in terms of efficiency. Yeah, but close to 20 is always better. And we can, yeah, if we are creating a report, I think I would use these overview details. Here. Okay, so make sure that if you are creating that report, because at the end you will have to submit a report, if I want to follow your calculations, I need this. Okay, so I need but finding the PV array, it's up to you. You see that it's quite simple. You go to Alibaba. If you are, if you want to support local American companies, you can go to Amazon, and I'm sure you can find PV panels. Yeah, probably you will find the same and at the same price. Okay. But we do need the yeah. So it's picture is not enough. You need to show me the yeah. So here we have dimensions, and this is just 100 watt. It can be because of the efficiency, or it can be because this panel is smaller than others. Okay, so that's why we need the watt per square meter or per unit of area, square inch. But you have to Google, you have to decide on one panel, and then you have to let me know the dimensions and the expected PV production. And then we can start comparing things. So now let's use let's compare how can we work with PV watts. This is what you are going to do in the test, in the quiz today. Okay, so you have to become familiar with PV watts. And first, we need the DC system size. This can be the outcome, or it can be the data. Okay, imagine that we have a 10 kilowatt DC system size, and we want to compare different, this is always 180 because it's south, and we want to compare different angles. I want to compare 10, the angle is 10, the DC system size is 10, and then I go to the results. And here you have the annual, this 11,805 or 11,804, well, rounds up or down. So this is the annual AC energy. The AC is the alternating current. Okay, so it takes into account the conversion between the DC and AC energy or electricity. What we need, what we usually need is alternating current inside the building. 99% of the devices run on alternating current. So that's why we have this. We don't have the DC production. And here we can analyze different things. If we want to analyze the annual one, or if we want to analyze the January or the monthly production. And this is interesting, okay? So in this case, we are analyzing DC size is 10 size. Kilowatts. The angle is 10. The yearly production is 11,805. And let's say January production is 645. And then July is 1,300. We are talking about kilowatt hour. Units are important, remember. Okay. And now we want to compare this to 40. We compare the same size, but the angle is 40 now. So let's do it. We go back to this. We change the system size is the same. Now the angle is 40. Remember that anytime you change something here, you have to click outside so that you have this green tick, because if you don't do it, it doesn't change anything. So make sure that you have this green tick. Then we go here, and now we can compare. With 40, the yearly production is higher. But what about the January? Even in January, it's higher. But in July, it's lower. Okay, so if we are analyzing these results, in terms of yearly production, probably this is better. But in terms of the production in July, this option is worse. Now, with this data, we can make a decision. Are we interested in the yearly production, or are we using the building only in summer? So if we are using the building in summer, 10 degrees is better than 40. If we are using the building only in winter, 40 is much better than 10. Okay, so now we can make decisions, and we can compare this with now this is horizontal, the angle is 0, and now I want to compare this with vertical. So the angle is 90. Okay, what do? Do I have a PV array with 10 degrees, 40, or what if I have a horizontal one or a vertical one in the facade? Let's find out. So here I will do this with 0. Okay, with 0, the total is 10,000. The January is 486, and July is 1,352. What about a vertical one? So the total is this. The January is this, and the July production is that one. Okay. So now, what do we do? Why am I doing this? Now we have another parameter that we don't have here. It's the money. Usually the cheapest thing is to use a horizontal array. Okay, so with an angle of 0, especially if I have a flat roof, if there's a flat roof, like there is in this building. Okay, what if I place all these in a flat roof? Is this a good decision? Well, probably from the economic point of view, it's the cheapest because we don't need another structure, and we can just place the panel on the floor, on the roof, and that's it. But with the horizontal, the yearly production, well, between this angle and the horizontal one, is it a big difference? It's not. Here I save the money with this extra structure that I need. What if I place it in the in the wall, like a vertical one? Well, the vertical has the lowest performance, uh, in July, and the yearly one, but it's the highest in winter. Okay, so that's interesting. If I want to use this building mainly in winter, a vertical grid is not a bad option because it has the highest performance uh, in winter, in January. Okay, so the horizontal doesn't have the highest performance in any category, but probably is the cheapest. Okay, so we're not here talking about price, but that would be another important parameter for this. So now it's your decision, but at least you have data. I have this and I can compare, okay, what is and I can talk to the client. Okay, what do you expect? Do you expect to have a zero energy building, or do you just want to have you want an efficient building? It's not a zero energy building, but you don't have to pay too much money up front. Okay, now we can deal with the client, we can deal with the company, we can deal with the municipality, we can look for subsidies, we can, I know, there are a lot of options. But first, we need data. So it's like, what is the angle? The angle, I don't know. Come on. Now you have a narrative. You can say, okay, with this angle, what are you looking for? When are you using the building? Well, I don't know. Probably in winter, because in summer we go to the coast and we spend summer with our family in Long Island. Okay, so you are not using this in summer. So forget about to increase the production in July. So you want to increase the production from September to May. Okay, so let's go over this and let's see what happens, not the total one, but what happens from September until May. And in June, July, and August, you are not in this town, so you are not interested in that. So there is not a straightforward answer to that question. What is the right angle? What is the... No, because there are a lot of things, and eventually we have price, and price, it's important. Okay. This is what you have to do, and I want you to practice now with PV watts, and that's why we have the quiz. So I'm going to